Hello, welcome to the last part of chapter 23, which is about the respiratory system. In this one, we look at gas exchanges, those being oxygen and carbon dioxide. Now, we've looked at pressure, how air gets in and out of the respiratory system in the lungs, and we've also looked at the structures of the lungs and all. Now we're going to look at exchange of gases. When we look at the exchange of gases, we're talking about partial pressures. Now, the partial pressure has to do with how much of a gas there is in a mixture of gases. So the air around us, the atmospheric air, is a mixture of gases. Largely, we understand this to be nitrogen, N2, and it's 78.6% um, of the air around us, okay, is nitrogen. And about 20% is oxygen. So the air around us has a pressure of 760 millimeters of mercury. So that means that nitrogen, being 78.6% of that air around us, its partial pressure is 597 millimeters of mercury. So 78.6% of 760. That number represents the partial pressure of nitrogen. Okay, so in other words, however much percentage of a mixture of a gas there is, okay, however much the gases, individual gases, make up that much in pressure as well as the percentage of molecules. You get the general idea. So partial pressure added together equal the total atmospheric pressure. So all those partial pressures added together equals 100% of the components of the air and also 100% of the component or the pressure of the air. Okay, so this is Dalton's law. The total pressure in a mixture of gases is equal to the sum of the individual partial pressures. All right. Now, partial pressures, as we call them, we're referring to not just gases in a gaseous state, okay, but gases also dissolved in liquids, in water. So they can have pressures in water in the fluids of the body as well. So they have partial pressures in the fluids of the body as well. And so what we have are called partial pressure gradients. Partial pressure gradients are what drives these exchanges of gases out of the body and into the air, out of the air and into the body. So gases will go from a region of higher partial pressure to a region of lower partial pressure. Gas moves from higher partial pressure to lower partial pressure until the pressures become equal. All right, so both oxygen and carbon dioxide, as they exchange across a membrane, across capillary, across the alveolar membrane, the respiratory membrane, they equilibrate. They reach the same level. Both carbon dioxide and oxygen. So looking at these partial pressures in the body, there is partial pressure within the alveoli. So the percentage partial pressure of oxygen are lower than in the atmosphere. So there's less oxygen inside the alveoli than there is in the atmosphere because we're extracting it and because there's a lot of carbon dioxide. There's actually a considerably higher partial pressure of carbon dioxide inside the alveoli than in the atmosphere, the air around us. Atmospheric pressure, atmospheric air. As it says there, partial pressures of respiratory gases stay relatively constant. The pressures that exist in the blood are reflective of those that exist in the interstitial fluid, which of course are reflective of those that are inside the cell. It's inside the cell where carbon dioxide is generated, oxygen is being used. All right, so the gradient has to be out of the blood into the interstitial fluid, into the cell for oxygen, and then out of the cell into the interstitial fluid, into the capillary for carbon dioxide. that's at the capillary bed. So as the blood gets to the lungs, it has to be oxygen out of the air across the membrane into the blood and onto the hemoglobin. So the pressure has to be that way to extract oxygen from the air. And then the opposite's carbon dioxide. The pressure has to be out of the blood across the membrane and into the air, which is the gas inside the little ball alveoli. All right. So those are the two gradients. Those are the two movements of gases. One systemically in the capillaries of the systemic of the blood, the body tissues, and the other in the capillaries that line the alveoli. Let me move this a little bit so we can read that better. So relative partial pressures of the body. Okay, again, I think that's the same one again. Yes, it is. Okay, so there it is, and you can see this in a graphical form here. We're looking at the exchanges of gases, right? So oxygen out of the alveolus into the blood, into the, okay, so same thing that I was just discussing right there. So there's the pictures right there. Now, how much of a gas is going to be in the fluids, all right? There are certain solubilities. Gases can dissolve in liquids. We've got, carbonated beverages, so carbon dioxide can dissolve in water, right? Um, Nitrogen dissolves in water. Fish and beings live from oxygen in the water, so it dissolves in the water. So gases will dissolve in the water. Okay, they have different solubilities in the water, and so the solubilities of these gases are indicated by a solubility constant. It's called, or solubility coefficient. Um, and so this determines the partial pressure. So Henry's law, at a given temperature, solubility of gas and liquids dependent upon partial pressure of the gas in the air. So the pressure of gas in the air, in the gas, the air above the liquid is going to determine how much partial pressure, how much of that is going to get into the liquid. Makes sense. And it also has to do with the solubility coefficient, because there's only so much you can get to go into a liquid. You can get to dissolve in a liquid. Okay. And of course, a gradient is the driving force, partial pressure. Gases vary in their solubility in water. Carbon dioxide is 24 times as soluble as oxygen in water. Nitrogen is about half as soluble as oxygen in water. So those numbers are variable, okay, depending on whatever gas we're talking about. So low solubility, constant, require larger pressure gradients to push the gas into the liquid. This is how nitrogen, when divers get the bends, the nitrogen under the pressure, extreme pressure of the water, deeper water, forces it, actually literally pushes nitrogen into their blood, into their fluids. So when they come up and that decompression occurs, the nitrogen doesn't want to stay dissolved anymore, so boom, it comes out of solution, which the solution is the blood and other fluids, and when it comes out, it turns into a gas and you get bubbles. So it has to come out much more slowly, very slowly. Anyway, and it does that hyperbaric oxygen chambers, hyperbaric chambers. So the movement of oxygen, the partial pressure of oxygen in the alveoli inside the little bubbles is 104 millimeters of mercury, right? In the pulmonary capillaries, it's only 40. So the blood, when it arrives, deoxygenated blood, when it arrives at the lungs, in the alveoli of the lungs, it's only at 40 millimeters of mercury. In the air above it, inside the alveoli, the air is at 104 millimeters of mercury. The oxygen in the air is at 104 millimeters of mercury. So you can see the gradient. That means that, of course, the oxygen is going to diffuse from the air inside the alveoli into the capillaries. All right. And it continues until blood PO2 is equal to that of the alveoli. So it goes from 40 to 104. Okay. So it changes. Now, the PCO2, partial pressure of carbon dioxide, the blood and pulmonary capillaries when it arrives is 45 millimeters of mercury. In the alveolus, all right, in the air inside the alveolus, it is 40 millimeters of mercury. Okay, so that means from 45 inside the blood to 40 outside, it goes across that membrane and into the alveolus until it reaches 40 in the blood. um, so the gas exchange, like it says there, this is called external respiration, efficiency of gas exchange at the respiratory membrane. All right. Um, Anatomical features membrane contributing to the efficiency. Again, because you have these bubbles, you get a very large surface area, so the blood can flow very slowly, just like it does through the regular capillaries. It flows very slowly, so it has a chance to exchange and do all of its exchanges and go through one erythrocyte at a time. Not one at a time, but lined up one by one next to each other. Okay. So you get a large surface area and a very thin thickness because the walls of the capillary are very thin and the walls of the alveolus are very, very thin. All right. So there's what we call the ventilation perfusion coupling. So ventilation changes bronchodilation. So ventilation is really the movement of the air from one space to another as a gas. That's ventilation. Perfusion is more of the supply of a specific gas. Okay, perfusion changes by pulmonary arterial dilation or constriction, arterial dilation or constriction. So, in other words, has to do with inside the blood. Okay, the perfusion has to do with the blood. Ventilation has to do with the air. Okay. Um, an example of something that affects this whole thing is emphysema. Now, in the case of emphysema, what happens is instead of all those bubbles you get at the end of the terminal bronchiole, you get like one big bubble. The elasticity of the alveoli is decreased. It gets broken down. So it just turns into almost like one big alveoli instead of a whole bunch of little ones. And it can't expand and contract very well. So the air doesn't go in and out of it. So you're not getting a very good ventilation inside the alveolus with emphysema. So you can see here ventilation perfusion coupling. So ventilation here has to do with how much air is getting in and out of the alveolus. Perfusion has to do with how much blood is getting into the arterioles and so the capillaries. Okay, together they determine how much oxygenation the blood gets, which makes sense. So that's external respiration, and we got what we call internal respiration. This is the exchange of the gases at the capillaries, the systemic capillaries. Partial pressure gradient again drives that process. So the partial pressure of oxygen in the systemic cells is 40 millimeters of mercury. Inside the capillaries, it's 95 millimeters of mercury. Remember what we said that it was 104 when it left those. We'll talk about that in a minute, how it gets from 104 to 95. But when the blood arrives at capillaries of systemic tissues, it is about 95 millimeters of mercury. Okay. And then the movement of carbon dioxide, again, similar kind of thing. It's lower. It's 40, okay, inside of the capillary, and 45 in the tissues around the capillary. So carbon dioxide goes into the blood in the capillary until it reaches 45, thereby transporting carbon dioxide into the blood from the tissues. So you can see here what happens here, changes in respiratory. So there's the carbon dioxide exchanges. So one side is systemic and the other side is pulmonary. Okay, but you can see here bronchial veins, deoxygenated blood enters oxygenated blood within the pulmonary vein prior to the return of the blood to the heart. So what happens here, why this gets 104 to 95, it leaves the alveolar capillaries at 104 millimeters of mercury. Then the blood, okay, that venous blood, it goes to the tissues of the respiratory system. All of that smooth muscle, all of those bronchioles, all the trachea and the bronchi, it goes to those, perfuses those with blood, gives them oxygen, and then the blood drains from those. The deoxygenated blood drains from those and mixes with the oxygenated blood that's coming off of the um, the alveoli capillaries. Okay, so it's coming off of those. So it lowers the oxygenation level of the blood from 104 to 95. All right. So the deoxygenated blood mixes in there. And that's what brings it down a little bit. So the oxygen transport. Blood has the ability to transport oxygen via hemoglobin. So here's a couple of numbers to remember. About all of the oxygen that's carried by the blood, 98% of the oxygen is attached to hemoglobin. So that means only about 2% of it is actually in the plasma, dissolved in the plasma, free in the plasma. So when hemoglobin has oxygen on it, it's called oxyhemoglobin. When it's given up its oxygen, it's called deoxyhemoglobin. Okay. So that's one way we measure oxygenation of the blood, perfusion. Normal reading, 95% oxygenated the blood. This is one of the measurements that we do for the COVID to see if the blood is the lungs are working well enough to oxygenate the blood properly. Carbon dioxide, on the other hand, gets transported via three ways. It dissolves in the plasma. That's about 7% of it. Remember, it's 24 times more solvent in water than oxygen is. It will be attached to hemoglobin. It doesn't attach at the same place the oxygen does. It has its own spot to attach to on the hemoglobin molecule. But 23% of the carbon dioxide travels through the blood attached to hemoglobin. It's called carbaminohemoglobin. And 70% of the carbon dioxide that gets transported through the blood is as a bicarbonate ion. All right, so you can kind of see here, increase this a little bit here, the size of this. So carbon dioxide gets converted to bicarbonate ion by something called carbonic anhydrase. So some of it will actually form on its own. So when carbon dioxide mixes with water, you get carbonic acid right here. So you get an acid and you get a bicarbonate ion. Bicarbonate ion helps to regulate the pH of the blood. All right. Hemoglobin then will transport oxygen molecules. It will transport carbon dioxide, and it will transport actually hydrogen ions as well. As you can see that they will attach to it. Each one of them has their own particular spot on the molecule that they attach to. When we look at this saturation curve, so each hemoglobin can bind up to 4 oxygen molecules. So the percent of saturation has to do with how many of these hemoglobin molecules in the blood are bound to 4 oxygens. Okay. It's what we call a saturation curve. What's the percentage versus what's the pressure of the oxygen. So the partial pressure of the oxygen here is 104. That's the maximum that it gets inside the alveolus. And so that's nearly 100%. You can see that's about 98%, very, very close. 98% right there. And then that forms this curve that changes as the partial pressure drops. Okay, so lower partial pressure means less as a percentage will bind to the hemoglobin. Okay, that's sort of what we were looking at before. So there's this what we call the hemoglobin saturation curve. Okay, um, so what happens then with this? Can use the graph to determine saturation at a given partial pressure. We also can apply this to altitudes, higher altitudes. Then the partial pressure of oxygen is different just simply because partial pressure of the atmospheric components, the atmosphere is different. So that means partial pressure of oxygen is going to be different. Um, at 55,000 feet, partial pressure for oxygen is 81 millimeters of mercury. 17,000 feet, it's half of that. Okay, so we get a hemoglobin saturation of only 75% when we look at that. So looking here at 40, right? So at a high altitude where the partial pressure of oxygen is only 40 millimeters of mercury, we get about 75% saturation of the hemoglobin, right? Um, so altitude affects it, partial pressures, as we say. Um, there's what we call oxygen reserve, the oxygen remaining bound to hemoglobin after passing through the systemic circulation. So in actuality, as it says there, only 20 to 25% of transported oxygen is released. We're talking about at rest. So the oxygen is picked up by the hemoglobin, carried through, but remains about 75% of that remains stuck on the hemoglobin. Okay, the hemoglobin molecule. Other things that will affect that. This is why that it goes to if you've taken the CPR training. I took that a while ago, and I'm overdue for taking it again. They taught us to only give compressions, and I had an experience of actually seeing somebody have a probably a pretty massive heart attack. I'm totally convinced that he died right there in the hospital. Died right there at the airport. Luckily, there was a nurse and a EMT, which were right there. They actually revived him. But that's the first time I'd seen anyone actually that sort of thing. And the EMT just pushed really, really hard on his chest. I mean, really hard on his chest. Um, because what's happening there is, and that's what can save somebody, because what you're doing is you're moving the blood, you collapse like that and your heart stops. Well, your blood still has 75% saturation in it. If you can keep that blood moving, you can keep the oxygen coming out and into the tissues and keep someone alive. You know, the tissues alive, sort of, by keeping the blood moving. And that's the point of doing that. Because you got 75% of the blood that's in somebody's body. It's not moving, but it has to keep moving through those capillaries, right? Because the capillaries equilibrate and it stops. If you can put fresh blood through those capillaries, the exchange keeps going, oxygen keeps flowing, that kind of thing. Anyway, uh, that's just my 2 cents. Um, so temperature has to do with it. The efficiency curve, the binding curve, saturation curve, and binding hydrogen ions has to do with it. So let's take a look at what happens then. Oops. Hemoglobin and oxygen release. Normally do this. Let me expand this a little bit so you can see this a little bit better. Boom. See this better. You can see here that at different temperatures, at different pHs, and at different temperatures, the saturation curve changes. So at any given partial pressure of oxygen, say 40 here, remember this is about 60, 43 degrees is about 60%. At 38 degrees, which is about body temperature, it's 80%. At 20 degrees, it's over 90%. It's saturated because the temperatures are different saturation curves. Same thing here with pH. You get about 80%. At any given point, you get about like 75, 90, 95% at any given point. So pH and temperature both change that. Just a little thing about ventilation now, hyperventilation and hypoventilation. Remember, hyper is too much, so you're breathing too much, more than you need to. Hypo, not enough. You're not breathing enough, you're not getting enough. So what happens? Carbon dioxide will build up if you're not getting enough ventilation. Remember, what we talked about in the last one is that the body breathing rate is set by looking at carbon dioxide. We think it's oxygen, and oxygen does affect it, but at most conditions of the body, it's doing it because of carbon dioxide. Too much carbon dioxide is building up. So the body wants to get rid of carbon dioxide. So in actuality, we breathe not to get oxygen, but to get rid of carbon dioxide. And NH plus in the same on the same breath. So there's a greater loss of CO2 from the blood called hypocapnia. Too much, and it's hypercapnia. It's too much ventilation, carbon dioxide leaves, H plus levels fall, pH rises, we get alkalosis. Okay, not enough ventilation, hypoventilation, carbon dioxide levels build in the blood, H plus builds in the blood, pH drops, becomes more acidic, acidosis. All right. And so the body responds, remember, the nervous system responds accordingly. We get acidosis from too much carbon dioxide, from hypoventilation. Then the body responds by breathing heavier and deeper to get rid of that carbon dioxide, to get rid of the pH, to get rid of the H plus, raise the pH and bring it back. Okay? And then vice versa. We get hyperventilation, right? Hyperventilation, too much ventilation, carbon dioxide levels drop, pH goes up, H plus goes down. We get shallower breaths and slower breathing to try to conserve the carbon dioxide in the blood and let it build up again. Okay, so remember these things that we're talking about. Hypoventilation is breathing too slow, bradypnea. Too shallow, hypopnea. Some of these other ones, hypoxia, low blood oxygen, hypoxemia, hypercapnia, hypocapnia have to do with carbon dioxide levels, right? So again, this is all just what I was just explaining to you. Okay. And of course, these all things happen during breathing. We increase our metabolic rate. We increase our carbon dioxide levels. They go up in the blood. Okay, they go up in the blood. H plus goes up. pH goes down. We breathe heavier and deeper to get rid of that excess, right? Along the way, we also get more oxygen because we're breathing in. It just so happens that we do, but we're not really necessarily trying to get more oxygen. What our bodies are trying to do is to get rid of carbon dioxide. All right. So that brings us to the end of chapter 23, and so the end of the presentation. And good luck studying, and bye-bye.